Okay, let's talk about first order linear differential equations. So here's what it means. It means a differential equation that can be put in this form. And I guess the important part is I've got a y prime sort of sitting by itself, and then the only way that y appears is that there's a function of x times y. Otherwise, y doesn't play a big role in this. That there's a y prime here, there's a y right here, and p of x could be anything. So p of x could be a complicated function of x. So the dependence on x could be complicated. The dependence on x over here could also be complicated. But the dependence on y is really not complicated. So anyway, it's anything that can be put into this form, and here's what we do. There's a specific strategy for solving ones like this. What I'm going to do is I'm going to multiply by this thing that we call I of x, which is the integrating factor. And I of x is e to the antiderivative of p of x. And when I put this up here, I mean any antiderivative. So there's no reason to put plus c. We can just say c is 0. So any antiderivative, there's no reason to put plus c up here. So you figure that out and you call that I of x. What we're going to do is we're going to multiply both sides by I of x. So I just rewrote the same thing down here, except everything has an I of x on it now. And now here's the miracle that is the reason why this works. What you get on the left is we're going to see it's the same thing as the derivative of I of x times y. This thing on the left I'm claiming is the derivative of I of x times y. Why is that? Well, we can check. I can do the product rule here. So I would do I prime of x, and then I would leave the y alone. And then for the other part, I would leave my I of x alone and do the derivative of y. So it would look like this. And then, okay, well, what's I prime? Well, I is this weird thing. So this I prime is, well, I have to do the derivative of this. So this is like the chain rule, right? So the derivative of e to the whatever is e to the whatever. So I've got that here. But because of the chain rule, I need to multiply it by the derivative of the inside. The derivative of the inside is this is the derivative of the antiderivative of p of x, which is just p of x. So that's the derivative of the inside. So this turned into this. That's what we just went over. So this turned into this. I've still got my y there, and this is the same. And then this thing, this e to this antiderivative, that's still just I of x. So this is still just I of x. This is p of x. Yeah, really on this line, nothing changed except I replaced this with I of x again. And what were we checking? It's easy to forget. We were checking that this comes out to the left-hand side, which it does. This came first and this came second, but it's all there. This is the same as this. So, like I was saying, and this is the magic of why this works, this left-hand side is the derivative of I of x times y. You don't need to remember this derivation in order to do this in practice. It always works this way. So now that we've noticed that, picking back up from this line, we notice that the left-hand side is the same as the derivative of I of x times y. So that equals the same thing on the right. This is the same thing. And how this helps us is now I can just integrate both sides. So if I integrate both sides, doing the antiderivative of a derivative just gives me, the antiderivative and derivative just cancel. So I just get I of x times y. When I do the antiderivative of this, I get this. And the antiderivative of this is whatever it is. It's the antiderivative of whatever it is. And when I do this, I do want to put a plus c. So I want every possible antiderivative, so I want to add a constant that could be anything when I do this antiderivative. And then we're basically done. We just solve it for y. I mean, assuming we actually want an explicit solution. If we're okay with an implicit solution, then we can just stop at this step. If I want an explicit one, it's easy enough. I just have to divide by I of x. So the important part to remember is what I of x is, first of all. It's e to the antiderivative of p, and p is the thing attached to your y. So that's important to remember, and that you're multiplying both sides of it. And also just remember that inevitably, if your differential equation is in the correct form and you multiply both sides by I of x and you do it correctly, inevitably the left-hand side turns into the derivative of I times y. If you remember that, you should be in good shape. So let's do an example. We're going to solve this initial value problem. So first of all, it's not really in the correct form. I'm not supposed to have anything on my y prime. I've got this x here. So I'm going to fix it. I'm going to divide everything by x. Okay, now it's looking better. So my p of x is whatever's attached to my y, so I would take everything, negative 2 over x. That's all my p of x. And of course, q of x is 2, but I'm less interested in that at this point. I'm more interested in p of x because, of course, I is e to the antiderivative of p of x. So that's where this is going. So I'm there. Okay. This antiderivative is negative 2 natural log absolute value of x, and like I was saying, there's no reason to put plus c when we're doing I of x. Okay, this is the thing that I'm going to multiply both sides by, but it often pays to simplify things. Now here's the deal. I've got an e here and a natural log there, and they really want to cancel each other, but there's something in the way. There's something that this negative 2 is kind of in the way here. What I can do is take this and use a log rule to put it up there. Like that. And now I've got an e to the natural log of something, and they just cross right off. One more thing, we don't like absolute values. They come up all the time, because especially when you find natural log of absolute value of something, that comes up all the time in calculus, but we don't like it. So as soon as I see an absolute value, I'm looking for excuses to get rid of it. And I see that this is raised to an even power. So an even power gives a positive answer whether you're doing a negative or a positive. So this is the same as x to the minus 2 or 1 over x squared. It's all the same thing. Yeah, so this absolute value was really not necessary. Anyway, finally, after simplifying this so much, I'm going to multiply both sides by that. And I guess I mean here. So I've got an x to the minus 2y prime minus 2. Okay, I'm taking an x to the minus 2, and this is another x on the bottom, so I'll call this x to the minus 3y equals 2x to the minus 2. So I multiplied this whole thing by x to the minus 2. And I don't care too much what's written over here. because I remember that whatever it is inevitably going to be the derivative of I times y. So this was my I, so it's the derivative of I times y. So it's like that. And now I do the antiderivative of both sides. So antiderivative of this is going to be, oops, I got a little ahead of myself with that negative. So this 2 carries right down, and then I'm just doing the regular rule for integrating powers. And at this point I should start writing plus a constant. And I can write it that way. So one thing is, this is an initial value problem, so we should be able to figure out C. So this is telling me that when x is 2, y is 0. So if I plug in those, this is going to give me 0. This is going to give me, let's see, 2 times 2 to the negative 1 is just going to be 1, right? So C is 1, and then I'm basically good. I can just write this, x to the negative 2, y equals negative 2x to the negative 1 plus 1, and I can call this my answer. This is implicit, because it's not solved for y, but it's easy enough to solve for y. If you really want an explicit solution, I would just multiply both sides by x squared and get that. So if the instructions don't say implicit or explicit, then you can just stop as soon as you have something. But it's easy enough to get an explicit solution.